recording the class. Last class, what I build how regression come into an existence, and I develop simple and multiple linear regression model. And I said simple and multiple regression model will be used when certain assumptions are satisfied. One of the assumption is response variable must be quantitative or continuous. Okay, and response variable, that means also the error, they have the same distribution, normal distributions. So they are normally distributed. This is what. Now my question is, this is the regression beta 0, beta 1, beta 2, x2i plus beta k, xki plus epsilon I. How can I put Poisson regression is in there? Okay, so last class I derived binomial distributions. Now I am going to derive Poisson distribution. Poisson distributions, this is the binomial distribution x equal to x, which is the mathematical formula ncx p to the power x 1 minus p to the power n minus x. This is the binomial distributions. I thoroughly discussed this distribution in last class. These distributions become Poisson distributions, which will take from e to the power minus lambda, lambda to the power x over factorial x under this. So under what condition? Number one condition is lambda equal to np. Number second condition is n goes to infinity. Number third condition is probability of success goes to 0. Under these three conditions, with mathematical operations, this mathematical form will take exactly that mathematical form. This mathematical form take exactly that mathematical form, which I am going to discuss now. Clear? So that you will be understand. Now, before that, I want to tell you what does this mean. In binomial distributions, that is the mean. Mean equal to NP. Okay? Mean equal to NP. Binomial distributions, mean equal to NP. And I put a conditions n greater than infinity and probability of success goes to 0 and goes to infinity. In realistic, what will be the example? Okay, first of all, try to understand what will be the example. Is there any example exist in real life? Yes, not only one, many. For example, in Macomb, most busiest intersections is the intersection where there is a train line goes and 4 or 5 line, right? So in that 4-way line, in 4-way intersections, how many vehicle, how many car passes by in 24 hours? Maybe altogether 100,000. Understand? In 24 hours, suppose in that busy railway station where there is a 4-way traffic goes by, suppose in 24 hours there is 100,000 vehicle passes by. Okay, so 100,000 is a very big number, right? Right? 100,000 is a very big number, and equal to good. And how many accidents are taking place in each day? Very low, right? Do you understand? So when your probability of success, that means number of accidents is very low, but number of occurrences is very high. What is the occurrences? Number of car passes by that intersections. In such a case, we are going to use Poisson distribution. For example, in a telephone exchange, how many phones come? Maybe 10,000 phones comes. How many of those phone call are like dropped out? Understand? Very few, right? Phone call drop. How many phone call you receive every day? Suppose a very busy person, he received maybe 300, 500 phone calls, but how many of them drops? Very little, right? So are you understanding that these assumptions, this is called the assumptions. Under these assumptions, we move from here to there. This is called the assumptions. we are going to use these assumptions in order to come up with the new distributions that has a name, Poisson distribution. It was mathematically derived by the French mathematician Denis Poisson. Clear, right? First of all, come into an existence. So this mathematical formula, it is not someone wake up in the morning and write a formula and then he said that, well, these two conditions are satisfied, so this is a probability distribution. No, this did not happen like that way. On the other hand, it come into an existence by the mathematical derivations. Please from next time come in timely manner, okay? Yeah, please come to the class in timely manner, because I already discussed something. I'm sorry about that. But class is recorded. I will give you the link. But please, my advice and request, very polite, humble, please come to the class in due time. Okay. So after that, as I mentioned these things, I give you real life example. Now it starts from there. Probability of x equal to x and cx p to the power x 1 minus p to the power n minus x, and then I want to write here factorial x and factorial n minus x p to the power x and 1 minus p to the power n 1 minus p to the power minus x. Okay, so as this is our assumption, lambda equal to np. This is I'm assuming. So our p hat, probability of success, equal to lambda over n. So we are going to plug it in there, n minus 1, n minus 2, up until n minus x plus 1, and then I have n minus x factorial and denominator factorial x n minus x factorial. Okay, what I did in here, this factorial n can be written like that way. Understand? Factorial n in the numerator can be written like that way, and then p equal to, I can put here lambda over n to the power x. I will assign homework next week after finishing negative binomial regression. 1 minus lambda over n to the power n, and then 1 minus lambda to the power n to the power minus x. So this is a lambda. So I have to put here, this is a lambda. This is 1 minus. Okay. So let me take that pen again. This that pen is sharp. Okay. So this and that cancelled out. This and that cancelled out. Okay. Now I want to do something in here. I want to put here lambda to the power x and factorial x is in here. This lambda to the power x and that things has been put it in there. Okay. These two things has been put it in there. Now I want to write like this one, and then I want to put here 1 minus, if I take here, okay, this is the n minus 1, n minus 2, up until n minus x plus 1. And then here I want to put n to the power x. This n to the power x, I put it in there. Now I want to put here 1 minus lambda over n to the power n, and then 1 minus lambda. This is the lambda to the power minus x. Now I should not touch this. I will make all the manipulations in there. So here is, if you take a look at this, altogether how many terms in there? There is n to the power x term in here. 1, 2, 3, 4. Here is, if you take the net, this common, then x minus 1. So x minus 1 term plus this one. So altogether x n term. So that could be written in this format: n over n, n minus over n, n minus 2 over n, and then it will go n minus x plus 1 divided by n. Clear? Please shut down your computer. The guy who is, please shut down your computer. So write the things that I'm doing. Yes. From here to here, or here to here? So black to in here? Okay. Are you seeing lambda to the power x in here? That is in here, okay? And n to the power x is in here. Okay? This x is in there. Okay? So these factorial x is in here, lambda to the power x coming from there. These two is in here. These things, factorial n can be written like that way: n times n minus 1 times n minus 2 times n minus x plus 1, and then n minus x. Clear that one? Right? Okay. So now, from here to there, now how many n is in there? There is 1 and 2 and 3 and up to n. Okay? Sorry, up to xn, up to xn. How many? How many? 1 and 2 and 3 and how many? So here is x minus 1. Okay? So take a look at that. If you compute all of these things, okay, let me explain these things more. Are you understanding how many n's in there? So n minus 1, n minus 2, n minus 3. Then here, n minus x minus 1, right? N minus x minus 1. So x minus 1. With that one, it will be x. 1, 2, how many? X minus 1. With this, then it will be x, right? I hope you understand this. Okay, so from there, I just want to write here y, and this one I just want to write here as a z. This is I consider as a y, this is what I consider as a z. Okay? So now if you plug it in there, lambda to the power x and factorial x, this is equal to 1. This is equal to 1 over 1 minus n, 1 over 2 over n, and this will go. Then it could be written as 1 minus x minus 1 over n, and then y, and then z. Are you understanding this? Are you understanding this? Online people, are you okay? Okay. So if this is the scenario, now we have to take what assumption? Limit n goes to infinity, right? That is what the assumption is, n goes to infinity. So now taking limit, now taking limit, we get what? If we take the limit n tends to infinity, then what will happen? This over factorial x, and this become 1. Next time, all of this become 1. And then we have in here y comma z. Do you agree with that? Because if n goes to infinity, then 1 over infinity equal to 0. 1 minus 0 equal to 1. 1 minus 0 equal to 1. So this will all 1, 1, 1. Do you understand that one? You understand that one? So now what I have? I have limit n goes to infinity, lambda to the power x over factorial x, and then y and z. This is what I have. Now I have to do what? Y equal to what? Y equal to 1 minus lambda over n to the power n. This is what y. Okay? This is what y equal to. So now if you take the log of y you get n log of 1 minus lambda over n. Okay? Now you can write log of y equal to n. Then you can write here lambda over n, lambda square over twice n square, lambda cube over 3 n cube. This is the logarithm series. So this is the logarithm series. 1 minus log 1 minus lambda equal to this. Log 1 minus lambda, this is the logarithm series. Clear? Are you understanding? This is just the formula. This part could be written like that. This is the formula. Okay? Now if you multiply by n, then what are you getting? You are getting lambda square 2n lambda cube 3 n square, and it will go by that. Are you getting it? Now if you take limit n goes to infinity log of y, then you are getting lambda. This part will be gone. Rest of the part will be 0. Right? N goes to infinity. Are you understanding? N goes to infinity. So if this is the case, then y equal to what? We have e to the power minus lambda, right? Log will be transferred to the right side. It will be exponentiation, right? This will be exponentiation. So that's the way we got this one. Okay. Now another one equal to z equal to 1 minus lambda over n to the power minus x. Clear? So now if you transfer it, 1 over x equal to 1 minus lambda. Clear? Now if you take the log in here again, if you take the log again in here, hold on. Z equal to that, let me see the z value. 1 minus 1 over lambda equal to x, then it is coming in there. Now, okay. If I take the log, we don't need to take the log. We don't need to take the log in here. If you just take these things, limit n goes to infinity, z 1 over x, then what I will have? 1, right? I don't need to take a log in there. I don't need to take a log in there. So, and then if you take a n goes to infinity in this format, then you are getting in 1 in there, right? Now, if you want to change it this format, z limit n goes to infinity, if you take like this way, z, then 1 to the power minus x, right? Right? 1 to the power anything is always equal to 1, whatever you put. 1 to the power 1 billion, 1 to the power negative 500, 1 to the power whatever you want to put, it is always equal to 1. Clear, right? Did you get it or not? My word. This is negative binomial. This is, yeah. So now what we got? We got y equal to, here we got, after plugging limit n goes to infinity, we got lambda to the power x over factorial x e to the power minus lambda and 1, right? This is what we got. And then after getting these things, if you write beautifully, then e to the power minus lambda, lambda to the power x over factorial x. Do you understand? So now let me show you. This is the final formula, derivation of exponential distributions from binomial distributions. This is the binomial distribution. By these assumptions, we end up with these things mathematically. Clear, right? So Poisson distribution is a mathematical derivation from binomial distributions. Clear? You understand, right? So we have successfully convinced you the mathematical formula for the Poisson distributions take this format. E to the power minus lambda, lambda to the power x over factorial x. Here x takes value 0, 1, 2, 3, 3 up to infinity. Okay, and lambda is greater equal to 0. This is the Poisson distribution. These distributions satisfy two conditions. So number one condition, probability function, this is greater equal to 0. Number two, sum of these equal to 1. Clear, right? Question, you have a question? Ask me question. What is the question? Which line number? This one? Where did I get this? You are talking about this one, right? Where did I get this? Okay. This is where, are you seeing? This is the binomial. This is that. That could be written like this and that. And this is the 1 minus lambda over and to the power minus x. Clear, right? Now two more things for these Poisson distributions then I will go likelihood functions and then Newton-Raphson method. After that, I will derive Poisson regression model. That will be the end of today's class. Okay? Understanding? So the rest of your life, someone will ask you how we understand like straight line equations and how a straight line equation is converted to a regressions in 1805 by the Galton, and then how multiple regressions is. But the next question will come to your head, how that regression come into an existence. So this is all the background I am now giving. Okay? Clear, right? Okay. Now let me show you this is equal to 1. This is a PDF I have to show. So sum of x equal to x, which could be written x takes value 0 to infinity, e to the power minus lambda, lambda to the power x over factorial x. If e to the power minus lambda has been taken and then x value is being plugged in there, this is 1 lambda over 1 lambda square over 2 lambda cube over 3. This will go all the way down there. What is this? This is equal to e to the power lambda, right? E to the power x formula is what? 1 plus x over factorial 1, x square over factorial 2, x cube over factorial 3. This will go all the way, right? Exactly same. Exponential series. This is the definition. There is no derivations, nothing is in there. E to the power x equal to 1 plus x over factorial, x square over factorial 2, x cube over factorial 3. This is the definition. You understand definition, right? This is just the definition, defined that way. Why they have defined an exponential series? When logarithm was defined, there was a base. Logarithm 2, logarithm 10, logarithm 5, logarithm 20, logarithm 15, logarithm 16. So someone write a paper in logarithm in there, and some other people have to find that logarithm table in order to get values. Understand? I'm talking about 100 years earlier, or at least 50 years earlier, when calculator was not invented. Calculator was invented in 1972, 70 or something like that. Okay. Before that, there was a big book, log table, exponential table, sine table, cos table. So people, scientists, they use that thing. So during that time, everyone said that, well, there is a different basis of log. How about we define a series, we call it as a exponentiation series or e to the power x. They define that like this way, and then they name it now any log that is e-based is a natural log. So if anywhere any paper written natural log, immediately they hit this is coming from that. Understand? So natural log means anyone in the planet, they immediately compute these things by following value of x in there. Suppose someone put x equal to 10 in there, if it go and certain stage, denominator is bigger than the numerator, factorial is bigger than the numerator, this series never explode. Are you understanding? There is a exponential series that is called exponentially faster. But that series, this e to the power x will never explode. Never explode. This series never explode unless you plug x equal to infinity. In certain like 3000 terms, you will go, the denominator term is bigger than the numerator term. Factorial term is bigger than the numerator term. For example, suppose I want to put x equal to 2. Let me explain you these things. X equal to 2 I want to put, then what are you getting? 2 over factorial 1 and 2 square, that means 4 over factorial 2, then 8 over factorial 3, and then 16 over factorial 4. Understand? Then if you put here 2, 32 over factorial 5. See, numerator is bigger than the denominator. This factorial 5 equal to 120. This is equal to 24. This is bigger than that. This is bigger than that. This is bigger than that one. So that means this will always converge. Understand? This is the basic understanding. So e to the power x is a definition. Clear, right? E to the power x is a definition. So like the way they define continuous function, limit, continuity, differentiability, those are coming from the definitions. If I have an opportunity, I can also discuss how the differentiability, all of those things work. Anyway, so I have proved this and that equal to 1, right? This and that equal to 1. So I proved this condition. This condition now has been proved, and this is also true. So if these two conditions are satisfied for any function, that function is called probability mass function, PMF, or it is called PDF, probability density function. Any function, you come up with any functions that satisfy these two conditions, then that function is called the probability mass function or probability density function. Clear, right? Okay. Okay, now I want to find the mean of these distributions. Expected value of X. Expected value of X, this is the formula that you know, right? Right? This is the formula of the expected value. So plug the value. X takes value 0 to infinity. X e to the power minus lambda, lambda to the power X over factorial X. Clear? I want to prove what is the value because this mean value is going to be used. So now plug in there e to the power minus lambda, we just want to take out there, and then these things is a X. I can write here lambda to the power X minus 1, and then I can write here X times X minus 1 factorial. X now goes 1 to infinity. Previously, X taking value 0 to infinity, as I take out 1X from there, so now it has become X takes value. I want to cancel this and that. I want to cancel this X with this X. Okay. So now what I have, lambda e to the power minus lambda, and then I have a sum, X goes 1 to infinity, lambda to the power X minus 1 over factorial X minus 1. So now if I plug the value, lambda e to the power minus lambda, then if you plug X equal to 1, then you get 1. If you plug X equal to 2, you will get lambda over factorial 1. 3 lambda square over factorial 2. What are you getting? Like this, right? So lambda e to the power minus lambda and e to the power lambda. So you have a lambda. Are you understanding? Are you understanding? So mean of the Poisson distribution is lambda. Lambda is the parameter of the Poisson distribution. Write it down. Lambda is the parameter of the Poisson distribution. What is parameter? Lambda is the mean of the Poisson distribution, which is also the parameter. Now, if I ask you, this is mean, what is the definition of parameter? What is the definition of parameter? What is the definition of parameter? Can anyone from online tell me what is the definition of the parameter? Parameter means unknown constant. Parameter means unknown constant. Unknown constant. Here it is also called for the Poisson distribution, X equal to X e to the power minus lambda, lambda to the power X over factorial X. This is also called the rate. Accident rate. On an average, 3 accident takes place. On an average, 2 phone call dropped. Rate, understand? Unknown constant. Traffic accident rate in Macomb busy intersection is lower compared to a busy intersection in New York, right? So that is an unknown constant. It varies places to places, circumstances to circumstances. Okay. So parameter means unknown constant. Parameter means unknown constant. So lambda is the parameter of the Poisson distribution, which is also the mean of the Poisson distribution. Clear, right? Okay.